In this video, we will be learning about the method of steepest descent, which is an iterative method in optimization. So let's just refresh ourselves on what an iterative method is. So we are looking to solve, say, f of x equals 0, and we're going to generate a sequence of guesses. So we start off at an x0 or an x1. Here, the superscript just tells us which iteration we're on. And we want our guesses to get successively closer and closer to an approximation. So the hope is that our sequence of approximations converges. And what it means to converge to a number r means we can make our sequence of xn as close to r as we want by picking n sufficiently large, which means just going far enough into the sequence. Formally, that means if we're given an epsilon greater than 0, an error tolerance, there exists an n, so think an index in the sequence, such that the absolute value of the difference between the nth iteration, xn, and r is smaller than epsilon for all n beyond that. So if we're given, say, epsilon is 1 over 100, we may say, okay, the 38th, if capital N was 38, the 38th x, so x38, would get us within 1 over 100 of r, and then the 39th, the 40th, the 41st, all of them thereafter would also be within 1 over 100 of r. So that's what it means to converge. So the hope when we work with iterative methods is that we come up with something that will converge to a solution of the problem that we're working with. So to think of the method of steepest descent, the first thing we need to remind ourselves of is the directional derivative. So this is something that we usually learn in our first multivariable calculus class. So given a differentiable function f, domain Rn, so it takes in an n vector and then spits out a scalar, a number, and a unit vector u in Rn. So remember what unit vector means. Unit vector means that we usually think of it as the 2 norm of the vector is 1. So it's a vector of length 1. So given a unit vector u, we want to think about looking in the direction of that unit vector u, slicing through the function and saying, what's the derivative of the function in that direction? This is our formula for that derivative. So the way we read this is the derivative of f of x in the direction of u is the gradient of f transpose u, or remember, written this way, this is the dot product of the gradient of f of x and u. Many textbooks will also denote this instead of this d sub u as this, gradient of f sub u, to say it's the directional derivative of f in the direction of u at x. And we want to think about our general optimization problem where we're trying to minimize f. And so we're standing at x and we want to take a step to a new point in Rn from x. And a question to ask is, what direction is most appealing? So we're standing at x and we are looking at all these different possible directions that we could step in. Well, one appealing direction is the direction of steepest descent. So think about it like the case where you have f of 2 variables, and you can think of it like you're standing on the slope of a mountain, and you want to say, which direction should I go in to go down? Well, think of it like being on skis. One natural choice is to point your skis in the steepest downhill direction, the direction of steepest descent. So what that means is that we want to minimize the directional derivative of f of x in the direction of u. It's helpful to remember this other formula for the dot product of 2 vectors. And so again, this is something that you usually learn in your intro calculus class, and you usually write it like this in calculus, where you would say you have 2 vectors a and b, and the dot product can be written as the length of a times the length of b times cosine of the angle between them. In this case, our vectors are the gradient of f at x and u. So we're going to think of, here's our gradient of f, and here's our u. And theta will be the angle in between them, the smaller of the 2 angles. Of course, you could also think of this angle, but we are going to concentrate on the smaller of the angles. applying this formula that we learn in calculus here, we know, because u is a unit vector, that it has length 1. The magnitude of the gradient, well, that's just whatever the magnitude of the gradient is. And remember, the idea is we're looking in these different directions represented by varying the unit vector u. So as we vary that, well, what changes in this expression? All the u's are unit vectors, so this is always going to be 1. But this cosine theta changes as we move this u around. So the question is, what's the smallest cosine theta can be? Well, remember that cosine of theta, if we graph cosine theta, we know it's this wave function here, but its range is the interval -1 to 1. So the smallest this cosine theta can be is -1. What does that mean for theta, the angle between the two vectors? We'll come back here. What's the smallest positive theta that gives us cosine theta -1? This value here, and we remember that that value is in fact pi. If you like to think in degrees, that's 180 degrees. That is the opposite direction of the gradient. How do we get the opposite direction of the gradient? As a unit vector, okay, here's the gradient. Divide it by its length, that makes it a unit vector, and then multiplying by -1 means it's a unit vector pointing in the opposite direction of the gradient. That is our direction of steepest descent, which also you may remember from your intro multivariable calculus class, because we usually learn in that class that the direction of steepest ascent at x is the gradient of f of x, and the direction of steepest descent just goes in the opposite direction. So think about the skiing example. If you're standing on the slope and you want to look at the steepest uphill direction, you turn your skis in the direction of the gradient. If you want the steepest downhill direction, you do a 180 and point in the opposite direction. That is the first step in the method of steepest descent, right? Which u do we want? Oh, we want the direction of the negative gradient. The next question is, how far should we step in that direction? And this is kind of a fundamental concept in what we call line search methods, of which steepest descent is one of the most famous. Line search methods. You pick a direction in which you will step from x to a new point in Rn. So once we pick that direction, the question is, how big is the step? And so that's what we need to now figure out. So we're going to step in the direction of the gradient of f at our current iterate xk. We want to look in that direction and make an optimal decision. So we're going to have some step size, t sub k. It's going to be a positive step size because we know we have a negative gradient that's non-zero. If it's non-zero. If it's 0, then we're probably at a potential for a minimizer. But if it's non-zero, it's downhill. Let's pick an optimal step size in that direction. We call it tk. So let's think about parametrizing the ray in that direction of the negative gradient. And this is how we do it. So we say for t greater than 0, we're standing at xk, and then we're going to move t units in this direction of the gradient of f at xk, the negative gradient of f at xk. So this parameterizes that ray in the direction of steepest descent. We are going to plug this in to our f, and that will restrict the function, the objective function, in the direction of steepest descent. And so that's what we have here. So this is our parameterized ray, and we plug it in to the objective function. Now remember, we want to pick some kind of optimal step size. Here, t is just some variable that's greater than 0. We want to pick the best value for it, which will give us t sub k. So we now have a second optimization problem in here, where we are now minimizing the objective function along this ray of steepest descent. This gives us the formal definition of the steepest descent sequence for minimizing objective function f. So We're at a current iteration, xk, and so remember that means we know xk. We know the gradient. We can plug in xk to the gradient of f. Xk plus 1 is this step of size tk in the direction of the negative gradient, where tk minimizes our objective function with the restriction that we mentioned on the previous slide. So the work will come in determining the best step size t, which we call, again, tk. So that gives us the official definition of the method of steepest descent. And like any optimization algorithm, these things become much more manageable and understandable when we look at an example. So let's look at this example here. Minimize the function f of x, which is 4x1 squared minus 4x1x2 plus 2x2 squared. And we're going to start with an initial guess of 2, 3. Our first step is to compute the gradient. So let's remember how to do this. Well, we need the partial derivative of this f of x with respect to x1, which is 2 times 4 is 8x1 minus 4x2. And then to get the second entry of the gradient, we need the partial derivative of f with respect to x2. No x2 appears here, so we get 0 for that partial derivative. Here we'll get negative 4x1, power rule here, plus 4x2. So we have the gradient, and now, of course, we want to evaluate the gradient at our initial guess of 2, 3. So we plug that in, and we see we get 8 times 2 is 16, minus 4 times 3 is 12 is 4, and minus 4 times 2 is negative 8, plus 4 times 3 is 12, 12 minus 8 is 4. So we see we get 4, 4. So that means we're standing at the point 2, 3. The direction of steepest ascent is in the direction of 4, 4. We go to negative 4, 4 for the direction of steepest descent. So we are going to now, looking in that direction of steepest descent, we restrict now our objective function to the ray in that direction of the vector negative 4, 4. So let's plug everything in. Again, x naught, our initial guess, was 2, 3, so that's here. Our gradient, 4, 4, is here, and our unknown is going to be to find the optimal step size in that direction of the negative gradient. So simplifying what's inside here, this becomes f of the vector 2 minus 4t and 3 minus 4t, which we see here. Let's visualize this. So we are initially here. This is our point x naught, and this is meant to depict the direction of steepest descent. And of course, the question is how far to step in that direction. So here is the problem that we have to minimize f of this, the function restricted to this ray in the direction of steepest descent. And the first thing we need to do is calculate the derivative. So this is, remember, f takes in an n vector and outputs a number. So this is outputting a number which is a function of only the variable t. So what we want, standard single variable calculus problem, take the derivative with respect to t and set it equal to 0. When we take the derivative with respect to t of phi naught, we can use this vector calculus version of chain rule. Remember how chain rule works for functions of a single variable. If you want the derivative of f of g of x, and both f and g are differentiable functions, then we think of this as take the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. This is a similar rule, where the derivative of the outer function, leaving the inner function alone, is the gradient of f, leaving that inner function alone. And then we're taking the dot product with the derivative of the inside function, which is going to be the vector of derivatives with respect to t. So we get the gradient of f at 2 minus 4t, 3 minus 4t, dot product with negative 4, 4 by this version of chain rule. What we are doing is taking our gradient and plugging in these values for x1 and x2. Now recall that our gradient of f was 8x1 minus 4x2 minus 4x1 plus 4x2. And so we see we are plugging in 2 minus 4t for x1, and we are plugging in 3 minus 4t for x2. And when you work this out, so first distribute that 8, right? 16 minus 32t. Now distribute the negative 4, minus 12 plus 16t. Okay, in the second term, distribute the negative 4, so negative 8 plus 16t. Now distribute the 4 in the second term, 12 minus 16t, dot product with negative 4, 4. When you work that out, you get negative 32 plus 64t. Again, this is not a surprise because we expected to get something that was just a function of t, scalar valued. Now that we have phi naught prime of t as negative 32 plus 64t, let's remind ourselves what we were doing. We were minimizing phi naught of t. Well, take the derivative and set it equal to 0. So if we set this negative 32 plus 64t to 0, we of course get t naught equals 1/2. This is the size of the step that we will take in the direction of the negative gradient. So for our next iterate, x1, we have, okay, we started at x naught, our initial guess. We are stepping in the direction of the negative gradient, the direction of steepest descent, with a step size of 1/2. Plugging everything that we just calculated in, x naught was 2, 3. Recall our gradient was 4, 4. Our step size is 1/2. Simplify this, right? 2 minus 1/2 times 4. 2 minus 2 is 0. 3 minus 1/2 times 4. 3 minus 2 is 1. So we are stepping to the point 0, 1. And so this is depicted here. Our new step is above the point 0, 1 here. So we have taken that step from our initial guess to the point 0, 1. And you can see that we have made a nice reduction in the objective. We didn't mention this in the beginning, but we do know that the global minimizer, x star, is of course 0, 0. So that is the point that we want to be converging to. Let's look a little bit more generally if we were to do a few more iterations. If we did a second iteration of steepest descent, we would go to the point 2/5, 3/5. A third iteration gets us to 0, 1/5. And here we're just reminding ourselves that global minimizer does in fact occur at the origin. Now, this depiction in the domain, so think now bird's eye view looking down at the domain. The objective function is this convex paraboloid above it, x naught, x1, x2, x3. What do we notice about the kind of path we're taking if we put all these steps together? Well, if we connect them, that was our first iteration of steepest descent. Our second iteration, our third iteration, hopefully what we're noticing here is that we do in fact have right angles in between the paths of the steps that we're taking when we apply this method of steepest descent. So this is kind of an interesting property of steepest descent. Formally written here, the method of steepest descent moves in perpendicular steps. Formally by that we mean if we take the vector joining xk to xk plus 1, that vector will be perpendicular to the vector joining xk plus 1 to xk plus 2. That is a formal way of stating what we see depicted here. But this is kind of interesting because what this means is as you move in the direction of steepest descent, your descent direction is getting worse and worse as you go further along that step until when you actually get to the new iterate, you are orthogonal to the new steepest descent direction. So this is a type of inefficiency that the steepest descent method has. And this is another way we can depict it. So now, remember, we're still looking from above at the domain, the x1, x2 plane, but what we now have depicted here are contours. or level curves of the objective function. Remember what that means. If you were thinking of this as a mountainside, or in this case a valley, if you were walking along this curve here, your elevation would be constant. Here, along this one, this would be also constant elevation, but lower than where we were at here. So with each step of the steepest descent method, we are moving to a new level curve at a lower elevation. But again, we're doing these perpendicular steps. So here, at this point, initially, we pointed our skis in the steepest downhill direction. That was this way. Then we saw the best step we could take in that direction was to get to this point here. Now, when we do the next iteration, we realize we need to turn our skis 90 degrees for this new steepest descent direction. And so we move in these perpendicular steps as we do our steepest descent direction. So this again is just another depiction. Here it's a little bit harder to see because now this is 3D, but we are doing this same kind of trajectory that we were looking at before. One question that we often ask when we look at an iterative method like this is, are there any situations where we know it's going to converge? One such situation here comes up when things are what we call coercive. So if our function, from Rn to R, f, our objective function, is coercive, which means the limit as the norm of x goes to infinity of f of x equals infinity. So this means as you are moving away from the origin, directly away from the origin, your vector is getting larger and larger. The function eventually takes off upward. If that's true, so our function f is continuous and coercive, then our f has at least one global minimizer. Further, if f is differentiable, then these global minimizers occur at critical points, so where the gradient of f equals 0. So if we have such a function, continuously differentiable, so we can do our steepest descent method because we need a derivative there, and coercive, if x0 is our initial point, and then we start generating our sequence of steepest descent iterates, then some subsequence of that steepest descent sequence will converge to a critical point of f. In addition, remember, we always like to think about what happens if our objective function is convex, because that's when everything is nice. If you have a convex optimization objective function, then your first order conditions become not only necessary, but also sufficient. And so in that case, where your objective function is both coercive and convex, then your steepest descent sequence converges to the unique global minimizer of f. So when things are convex and coercive, you get this really nice payoff. And when you think convex and coercive, you could have, so let's just do something simple where you have a function of one variable. A function like this would be coercive because as you move away from the origin, eventually the function takes off. But you have this issue of, well, if you're doing some type of iterative method to find a global minimizer, you could get caught in that local non-global minimum. But if it's also convex, well, you can't have this because this point here would break the definition of convexity. So if you have convexity, well, then you have something that looks more like this, and you can't get these local non-global minima, and this is the case where steepest descent is going to find that global minimum for you. So this is the method of steepest descent. It is one of, I would say, the most popular two iterative methods in nonlinear optimization, the other being Newton's method. So understanding this really is critical in understanding how line search methods work in nonlinear optimization.